All right, everyone. This lesson, super important. And this is kind of a culminating part of all this accumulation. So it's again, more accumulation. We've been building this. But now the way it's going to work is I'm going to give you two rate functions, a rate in and a rate out. What does that mean exactly? I think I'll clear that up on the second example. I want to do an intro example real quick. So that way you can see how it compares to what we've been doing to what we're about to do. So let's say I have an intro example. We'll have this function j prime of t. Here it is. It's 2t minus 3 is the rate at which Mrs. West liked Mr. West with t in months, and we'll say j of t in love points. And I gotta give you an initial condition. J of 0 equals 0, obviously. So we'll say that her feeling towards me was neutral when we met. So kind of a silly example, but I think this can really highlight some of the things I want you to pay attention to. So I could ask all kinds of accumulation questions. I'm not really going to right now because we've done a lot of this already. I have a rate. This is the rate function. And I have an initial condition. So I could ask you a question like, for example, find j of 1. So find j of 1. So to do that, we know it's initial condition plus accumulation. So j of 0 plus the accumulation from 0 to 1, j prime of t dt. And we're going to use Desmos. I'm not going to touch the graphing calculator until next lesson. Next lesson will be an entirely calculator, no new math. Instead, just translating all of this to a graphing calculator. So 0 plus accumulation from 0 to 1. I'll have to put the function in. We'll do that in a second. Be careful. So I'm going to use that derivative notation, d of t dt for derivative. And then I'm going to say what the derivative function is. D of t is 2t minus 3. Okay. So what's going on? Well, there's the derivative function. Here is the accumulation. What do you notice that this value of negative 2 means? So negative 2 love points. That means her level for affection for me dropped. And that's true. After we first met, I did a funny joke and she didn't appreciate it and she hated me at first. True story. And then eventually we turned the tide a little bit. If I really wanted to, I could come up with a much better function that actually modeled it. Really, I just wanted to show you that we started out with a negative thing and then hopefully it turned around. Hopefully we didn't continue having problems. Like for example, let's say after 5 months, where were we at? That would be j of 0 plus the accumulation from 0 to 5, j prime of t dt is equal to, and then we could just change this, 5. Hey, look at that. She loves me. So if you notice what's going on in this problem, if you look at the graph, this is the derivative graph, remember. We have negative area, which means from 0 to whatever this value is, 1.5. I'm accumulating negative area, which means the value's dropping in the original. In the original love function, my wife went down, which makes sense. If this is linear, the antiderivative would be a quadratic. It went down, 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 meaning she didn't like me. Then we hit a critical point, otherwise known as a root of the derivative. Then she started to like me again, and it went up, 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 and then I won her heart. We're married, been married for many years. So this situation had one rate function that changed from decreasing to increasing. I'm going to say that again. One rate function that went from decreasing to increasing. That's how accumulation works when you have one function. It can change at different points. So it can go down, it can go back up, we can accumulate positive, we can accumulate negative. The total can go up and down based on the one rate. So how is that different from what we're about to do? Now, we're going to have an accumulation problem with two rates. This is the same ideas, and actually it may be a little bit easier because you don't have to figure out where things are changing, kinda. You'll see it in a minute. But basically, we're going to have two rate functions. So an example that we're going to use right now is we're going to say Mr. West has a math club. So Mr. West has a math club with 2 students at t equals 0. Okay. The rate at which students enter the club is modeled by the function, and we'll just give you the function. I like to use E for enter. They can call it whatever they want, but we'll say E of t equals 2e to the t over 5. So students enter the club at this rate and leave the club at a rate modeled by this function L of t for leave equals natural log t plus 3. T in days, and then obviously it's number of students for the total. Total is number of students. All right, lots of information here. But everything we've been doing with accumulation is still going to factor in. It's going to look very similar. So right off the bat, the first thing you should do, and when we give graphing calculators, I will show you how to do this. But while we're learning it, especially in Desmos, I love Desmos for these types of problems because you can do everything in line by line by line Desmos. I love Desmos for these types of problems. This is why we've been so involved with Desmos for these types of things. I'm going to graph the e to the t function. E to the t function. 2e to the t over 5. That's my entering rate. It's the rate at which people are entering. My leave function is natural log t plus 3. Okay, so students are coming in, students are leaving. And then there's 2 students to start. So a couple things right off the bat. A lot of times I can ask you a question like this, part A. Typical part A question is, how many students joined in the first, let's say 4 days? Okay, so all I'm asking is how many joined. Obviously kids are joining and kids are leaving because we have this out function. But the point is, we have one function that's not going to change from up to down. It could change, meaning it's not going to go positive to negative. It's going to be one function that is either always one derivative function that is always above the x-axis or always below. And typically they'll both be positive, and you'll see why and how we handle the out rate in a second. So how many students join in the first day? Again, if I want to figure out how many join, I'm going to do initial condition plus accumulation. Now, before we do that, I think it's very helpful to define. So one other thing. Let's do something that I want you to do every time, especially when we're doing Desmos. It's hard to do this on the graphing calculator, but this is one of my other immediate things you should do. It's called create a total function. And we'll call it t of x. So eventually we're going to have this total function. That's going to tell you the total amount of students at any given time. But we'll come back to this total function. So basically you're going to have these 3 lines right off the bat. Let's go back to part A, what I asked. How many students joined in the first 4 days? Well, if I wanted to figure that out, it has nothing to do with how many students started. All it has to do with is how many students I accumulated in from time 0 to time 4. So that is just a straight accumulation from 0 to 4 of your enter function. And that's it. No initial condition, nothing to do with the out function. So we would do accumulation 0 to 4, e of t dt. Cool. So 12 students joined. Round. I know it's not perfect. So on the homework, I tell you to round. 12 students. Nice. 12 students joined my club. So I had 2, I got 12. But let me ask you this question. While that was going on, some students left the club too. So B, how many students left in the first 4 days? So we're gaining students, but obviously not everyone's going to like me that much because I'm very mean. So students are going to kind of leave too. So we have this out rate, and we can accumulate that too. So if we accumulate the out rate, we can figure out how many students are leaving. So we'll accumulate, and we can just do as simple as change this to an L. Bam. Oh no, we lost 6 students. So even though we gained 12 students, which means we had 14, we lost 6. So how do we put all this together to answer a very, 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 very important question? Like, what is the total number of students at t equals 4? So on the 4th day, how many students are actually in the club? Since I created this total function, essentially what I'm asking you is to find t of 4. So the reason I say create a total function, meaning we'll just say, all right, the number of students at any time is represented by big T of x, is so that we have a way to talk about the total number of students. All right, so this is, again, kind of like the last problem where I wanted to figure out how much my wife loved me at any given time. It was initial condition plus accumulation. It's going to be the same thing here. So to find T of 4, it is still going to be initial condition plus accumulation out, or sorry, accumulation in, because I want to talk about all the students I'm adding to the club. But are you seeing where I'm going with this? You're going to have minus an accumulation out. So this is where calculus starts to get really useful, because you can start talking about a whole and how it's changing as things come in and to go out. And you can still talk about the total amount of something at any given time if you know the rates. This is a really big type of problem when you're filling a tank. So if you're filling a tank with water and you're also draining water or something like that, you can figure out the total amount if you know the rate at which things are coming and going. You know, for example, the rate at which people hit, so in real life, someone that does traffic analysis, the number of people that hit a light at any given time, and then the number of people that go through the light at any given time. You can figure out the total number of people sitting a light, and you can make decisions based on, you know, if the light has too many people backed up or too few about when to change the lights. So a lot of this type of dealing with different rates and how to total them is a huge part of making strategical decisions. So let's begin to build this total function. The initial condition is always going to be whatever they gave you. I gave you the total at time 0. So now we have a way of talking about how many students there were at time 0. Plus the accumulation in. So if I wanted to know accumulation in, it would be from 0 to 4, in this case, of your entry function, accumulated rate, minus your accumulation out over the time period. And that's going to give you the total number of students at time, we'll come back to that one, at time 4. So ready? T of 0 was my 2 students, plus the accumulation in from 0 to 4, E of t dt, minus, we have to talk about the students that left, the lame ones that didn't want to be in my super sweet math club. And that's going to give you a total number of students in the club at time 4, which was 8, which makes sense because 12 students added and 6 students left. So that's 6 plus the 2 I had. So it should kind of match up with everything we already found. So at time 4, I have 8 students. That's how you accumulate with a rate in and a rate out. Initial condition plus accumulated rate in minus accumulated rate out. Okay, so this is the important stretch that I'm going to want you to make, especially when we're using Desmos. And even though we won't use it on the graphing calculators, if you can do this every time, it makes these problems way easier. So we're going to go back to this total function I tried to create. Take a look. When I made this total function, I had the initial condition t of 0 plus the accumulation from 0 to 4 minus the accumulation from 0 to 4, because I was trying to find what was happening at time 4. Can I generalize this? Definitely. Here's how you do it. You do t of, I use x. The reason I'm not using t here is because t is my dummy variable already in the problem. You don't want to use t here for this x, because then you're going to have major problems with it trying to plug t in where it's not supposed to. So that's why, yes, it's a little weird that I'm using x outside, but the reason is I'm using t inside. In theory, you could put x's in the e and l function and have t outside, but at the end of the day, I think it's easier to make a t of x function. So t of 0 plus accumulation from 0. Everything here is going to stay the same, but do you see what's different? Instead of having the top bound before, I'm going to leave the top bound as my input. I'm going to use accumulation functions, create my own accumulation functions, so that I can plug whatever I want in. So watch how cool this is. In Desmos, you can say, okay, t of x equals t of 0, which was 2, plus everything on this bottom line. Get rid of the 4's and make those x's. Desmos can actually put this together. Your graphing calculator does not. I mean, it can, but it takes forever. Desmos can put this together and check out what you've done. You've actually created the function and shows you how many students are in the club at any given time. So back to that question of how many were in the club at time 4, there it was. It was 8. It's actually giving you any output. But then if we didn't want to look at the graph, we could say, okay, how many people in the club at time 4? Oh, people in the club at time 4 is 8. So this is called the total function, where you keep the top bound general so that you can input whatever you want in terms of figuring out how many total you have at that time. So that's where we created the total function. Some other things that you'll have to do in these types of problems. One thing to do is figure out, I'm going to undo this one. Now it doesn't really come up in this problem, but because we have more students entering than leaving. Oh well, that's fine. We'll leave it like that. There are some other things I'm going to ask about in the days to come. It doesn't really work out with this problem, but sometimes the rate at which people enter and the rate at which people leave, they flip. And I ask you about this in the discussion. This example is not very good for doing this, but let's say, well, I'll leave it to the discussion. The discussion is one of those times I'm going to ask you about it. I think this is enough for you to start on the homework. Let's take a look. So I think I'm done. I felt like there was more, but maybe not. Sorry, should have had this up. But I feel like it was shorter than I thought it was going to be. So let's see what I'm missing. So in the homework, problem 1, I give you a happiness function. And I'm asking, is my happiness level increasing or decreasing at t equals 4? Okay, so going back to this problem, it'd be like me saying, is the rate at which my wife loves me increasing or decreasing at 1? You plug into the rate function. So you plug into the rate, and if it's positive, that means her rate is increasing. And if she hates me, it means the amount, I should say amount. The amount is increasing, and if the value is negative, it means the amount's decreasing. When does it change from increasing to decreasing? For the wife example, that was at time 1.5, where it went from below to above. How happy is Mr. West at t equals 12? That's accumulation. And then when was I most happy over the interval? And it's just an absolute max. So you're going to have to go through and find the candidates, the endpoints, the critical point, and all that. Okay. The rate at which students enter a classroom. So it's just like the club example. 2 functions. And how many students entered, so that's just an accumulation in. Is the total number of students in the room increasing or decreasing? Okay, so that's the question I wanted to ask. Another question I can ask. And this one is going to come up. And then this example is not great for it, but the homework example is really good. Is the number of students increasing or decreasing at t equals 2? It's a good question. Other than that, the rest is on the video already. Okay, so this last question. Is the number of students increasing or decreasing at t equals 2? Well, back in the example where we only had one rate, you just plug it in. And if you got a positive answer, it was increasing. If you got a negative answer, it's decreasing. But how do you do it when you have 2 rate functions? Well, one way is to talk about the overall rate, and this is kind of my preferred way of doing it. That's your enter at time 2 minus your leave rate at time 2. So the enter rate at time 2 minus the leaving rate at time 2. And then everything still applies. So if you do E of 2 minus L of 2, you can see that the rate is positive. This overall rate is positive. So this would be a students per minute or day. Sorry, students per day because it's per day. Since it's positive, that means the total is increasing. Even though some students left on this day, more students joined than left. More students joined than left. So that means the rate at this time is increasing. Another way to do it is literally just to look at E of 2. So the rate at which students were entering at time 2 was about 3, and L of 2. And see that rate and compare. The join rate is much higher than the lose rate. So overall, more students are joining than leaving. Okay. So at the end of the day, the things to pay attention to, going back to this first example, when you have one rate function, they'll usually talk about it as a derivative. They'll say, okay, J of t is this function. That's how much my wife loves me. And then I give you the derivative of it, which is the rate. Typically, when you have 2 rate functions, they don't give you a total function, which is why I say create a total function. And then just pay attention to the fact that these 2 things they gave you are rates. The E of t is the enter, the L of t is the leave. 2 rates, you have to accumulate them to get totals, and I think it's very helpful to create a total function in Desmos. And then use it and keep it general. All right, so we will be working on this again using our calculator the next day. All right.